In our singular objective here for this lesson, we're going to be representing functions with Taylor-Maclaurin series. And I have it on pretty good authority that that is the exact requirements to become a Swiftie. So by the end of all of this, you will be an honorary member of the Taylor Swift Super Fan Club. Yeah, well, kidding aside, let's review the definition of a Taylor polynomial. So remember that your function has to have at least n derivatives evaluated at c, c being your center point. And if that center point is 0, we call it the Maclaurin series, or the Maclaurin polynomial, I should say. All right, and then this is what the polynomial looks like. We've seen this thing before. And each one of the terms has this form over here, where we're taking x minus your center point raised to that nth power and the coefficients of each one of those terms. You're evaluating your derivative. So here's the nth derivative evaluated at your center point and then divided by the nth factorial. So again, Taylor polynomial is going to end at some place. And over there, there's Mr. Taylor, Book Taylor in his pajamas. I guess he's reading right before bedtime, let's say. Okay, anyway. So what we're going to do, of course, is that we're just going to not stop right there at n terms. We're just going to keep going. We're going to turn this thing into a series. So speaking of series, the last lesson we defined a power series. And we're also centering this at some constant c. And if you take a look at the expansion of this power series, it looks pretty similar to the Taylor polynomial. Big difference, of course, is that this one just keeps going. But look at this x minus c raised to some sort of power. That's exactly the same as it was in the Taylor polynomials. And then you have some sort of coefficients right here, this a sub n. Those are the coefficients of each one of these terms, which we said those things could also be a series, and here were some examples of all of those. And so there is another connection between the definition of a power series and the Taylor stuff that we just looked at, and here it is. It's established by this theorem. So, boop-a-doop. If f is represented by a power series, f of x is equal to, and then there's the, the generic power series definition, for all x in an open interval I containing c, then, these little coefficients here, this a sub n, guess what they are? That's right. They are the nth derivative evaluated at your center point divided by the nth factorial. That looks real familiar. And also your power series looks just like this, which, man, doesn't that look like the Taylor polynomial, except for you just keep going? Because it is. These are the Taylor coefficients, and then, of course, that is your Taylor series. So our nth degree Taylor polynomial would have just stopped at a certain number of degrees, and then this one just keeps going. So basically what this is saying is that those power series that we found before that converged to our function, they were actually Taylor series, and we can form them the same exact way that we formed our Taylor polynomials, but we want to kind of generalize it so that we have an nth term and then we can add them all together because, that's what you're supposed to do with series. So here then is the definition of a Taylor series. If a function f has derivatives at all orders at x equals c, so in other words, you have to be able to take derivatives forever. You could do that with exponential functions, sines and cosines and stuff like that, sure. Then the series, so this looks just like the Taylor polynomial, but it's established as a series. So we have the infinite sum from n equals 0 to infinity of the nth derivative evaluated at c divided by n factorial times x minus c to the nth power is equal to blah, 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 right, is called the Taylor series for f of x at c. And of course, if c is equal to 0, then it gets its special name, the Maclaurin series. And, as far as it goes, these are our favorites anyway. We prefer these because it's so much easier to plug 0 in. That doesn't mean that we're not going to be doing some of those at some point in our lives. But as far as the ones that we need to have memorized go, they're going to be the Maclaurin series, centered specifically at 0. So, how do you make a Taylor series? Let me tell you. The way that you, oh, I think that's called the Maclaurin series. The way that you make a Taylor series is, you start with, oh, look at these big old numbers. Step number one, you just take lots and lots of derivatives of your function, right? Okay, so here's some derivatives of e to the x for you. All right, next, you're going to evaluate each one of those derivatives at your center point. And hopefully that center point is 0, because then it's like real easy. Like this one, this one, this one, this one, this one, this one, and this one. Okay, and then next you got to find a pattern here. So you got to find a pattern in order to write your nth degree term, so you can write your little summation notation. So something like this. So this looks like, if this is, let's say, n equals 0, this is n equals 1, this is n equals 2, and n equals 3, then I can see pretty clearly that this is x raised to the nth power over an n factorial, and so that I can write my summation as f of x is equal to the sum from n equals 0 to infinity of x to the n divided by n factorial. There is the Taylor series for e to the x. It's fabulous. Now there's one last thing that you need to do, and that is to find the interval of convergence. So this function is equal to e to the x, but where is it equal to e to the x? So in order to find that, you have to use the ratio test, of course. Perform the ratio test and see what that interval of convergence is. And we're going to do that for this one in just a little bit, but I think that's enough for this video.